going to be explaining rectangular waveguides. So let us start with the basics of rectangular waveguides. Okay, basics of rectangular waveguides. Waveguide is a hollow metallic tube with a uniform cross section. So if we are talking about a rectangular waveguide like this one here, so what we mean is that this is a rectangular hollow metallic tube from here. We have it in three axes, the X, the Y, and the Z axis. A waveguide is used to transmit EM waves using successive reflections from linear walls of waveguide. Rectangular waveguide has less attenuation. This less attenuation loss compared to transmission line. That is why waveguides have been increasingly, the use of waveguides have been increased of recent years. Now they use more waveguides compared to transmission lines because of the less attenuation less that are there in waveguides. And we have rectangular waveguides allows only TEM and TM modes. It does not allow TEM mode. It does not allow electromagnetic modes. It only allows the TE and the TM mode, where M and N can be either 1 or 0, and they can be used to identify the other. Then we have dominant mode in rectangular waveguide. So this is the dominant modes. We have here we have M is equals to 1 and N is equals to 0. So we have TE 1 0. So now we are done with the basics of rectangular waveguide. Now let us go to the cutoff frequency and cutoff wavelength of rectangular waveguide. This one is not empty. Okay. Now we are going to first of all look at the equations for the cutoff frequency and the cutoff wavelength. Looking at this rectangular waveguide, if here you send in a signal from here, you can get the cutoff frequency FC, which is given by C by 2 square root of M by A all squared plus N divided by B squared, where M and N can define the order and the mode. From here you saw that the dominant mode in rectangular waveguide is TE equals to 1 0, meaning that this M and N 1 and 0 can define the mode and order of the waveguide. And then lambda C, which is the cutoff wavelength, is given by 2AB divided by this, and this is the formula for here. Now we can take an example. We can use the dominant mode we took, where M was equals to 1 and N was equals to 0. So using that M and N, we can find the cutoff frequency and the cutoff wavelength. So if you substitute 1 and 0 here, we are going to have the cutoff frequency to be C by 2A, and the cutoff wavelength for the T, it should be 2A. Based on the order of mode, we can identify lambda C and lambda C and FC. So based on M and N, we can identify FC and lambda C. Now we are going to talk about the conditions for wave propagation. So we have two conditions. First one is lambda must be greater than lambda naught, where lambda C is the cutoff wavelength. Lambda naught is the operating frequency. So here is the cutoff wavelength. And here is the operating wavelength. Also, we can have FC should be less than F naught. You know, lambda and F, they are inversely proportional to each other. So FC should be less than F naught, where FC is also the cutoff wavelength, and then F naught is the operating wavelength. So from here we have understood the cutoff frequency and the cutoff wavelength of a rectangular waveguide. Now we are going to move into checking the different modes in a rectangular waveguide. So in checking the different modes in a rectangular waveguide, we have a statement to make: the lowest cutoff frequency or highest cutoff wavelength. So we are going to take the lowest cutoff frequency or highest cutoff wavelength. We have TE 10, we have TE 01, we have TE 11, we have TE 21, we have TE 12, and we have TE 22. So this is the lowest cutoff frequency So after checking for this lowest cutoff frequency, we move to check for this, and we move to, so this trend, the cutoff frequency keeps on increasing. And as you increase the mode, because these are different modes, as the modes are increasing, lambda decreases. So this is for TE wave. Sorry, I forgot to mention that for TM wave, we don't have modes. We only have for TE and TM. So if this is for TE waves, we can do for TM waves. But TM waves, we have one special thing about TM wave. For TM101 and TM01, we don't have, their modes are not possible. So let me get done with this, and then I explain that one. So we have these two, we don't have modes. Why don't we have modes? Because they are even sense modes. So we cannot have their modes. Now let's go to the next thing. Intrinsic wave impedance of rectangular waveguide. So we have intrinsic wave, we have for TE and for TM. So here I'm going to give the formulas. We have TE is equals to 12 pi divided by square root of 1 minus FC by F lambda squared. Here we can see FC by F lambda squared should be equals to sine theta. What is sine theta? Sine theta here is the tilt angle. Similarly, we have T for TM is equals to 120 pi. Sorry, this is pi. Forgive my bad writings. Which is equals to 120 pi cos of theta. And here we have the same thing, FC by F is equals to sine theta. Now we are going to go to the last thing for today's lecture notes, which is phase velocity and group velocity of a rectangular waveguide. Now for phase velocity of a rectangular waveguide, we're going to write the equation Vp is equals to C divided by square root of 1 minus Fc by F lambda squared. This is in terms of F. We can also write this equation in terms of lambda. In terms of lambda, we are going to have phase velocity equals to C divided by square root of 1 minus lambda naught by lambda C all squared. Now from here we can go to group velocity. Group velocity Vg is equals to C square root of 1 minus Fc by F squared, which should be equals to C 1 minus lambda naught by lambda C all squared. So now we have gotten the phase velocity and the group velocity. We can combine these two equations to get the relation between the phase velocity and the group velocity. And when this is done, we are going to have Vp Vg be equals to C squared. So this is the end of our today's lecture, and I'm going to brief you again on what I had today. We are going to have a small recap of everything so that we don't forget everything. So we started with a rectangular waveguide. If you can remember very well, I said a waveguide is a hollow metallic tube with a uniform cross section. And since we are dealing with rectangular waveguides, I said that this rectangular waveguide here, it's a hollow metallic tube. It's a rectangular hollow metallic tube. Also, I mentioned one thing. I said one important fact: rectangular waveguide has less attenuation loss compared to transmission line, which gives the reason why of recent we use more waveguides than transmission line, because their attenuation loss is very, very little compared to that of transmission waveguide. Also, I mentioned that in rectangular waveguide we are going to have two modes, which is TE and TM. We don't have the TEM mode. So throughout we spoke about TE and TM. So in some exams they might ask you about the modes for TEM. In that case, your response should be it does not exist. Okay, so after that we spoke cutoff frequency and cutoff wavelength of rectangular waveguide, where I gave the formula for the cutoff frequency, and this was the formula. I gave you the formula for the cutoff wavelength. I also went further to take an example of a dominant mode. In the example of dominant mode, I used m equals to 1 and n equals to 0, and after that I got fc equals to c by 2a and lambda c equals to 2a. Sorry for that. I also spoke about the conditions for wave propagation, because if you send in a wave, you have to know, is it going to propagate or is not going to propagate. So I gave you two conditions, one in terms of lambda and one in terms of frequency. So you can go through the lecture video. It's very short. You can go through it to understand what actually happens here. I proceeded with checking of modes in rectangular waveguide, where I said that we check from the lowest cutoff frequency or the highest cutoff wavelength. So we took an example here with lowest cutoff frequency. So we started with TE10, which was the lowest cutoff frequency, and we kept on increasing to TE22 mode. And I also mentioned one thing: as the modes are increasing, the wavelengths are decreasing, because we took frequency. As frequency is increasing, wavelength is always decreasing. So I also make mention of one thing: there are no modes in TM10 and TM01 because they are even sense modes. So these two, the modes are not possible. So we only have to deal with these remaining ones. Okay, from there I went further to talk about intrinsic impedance of rectangular waveguide, where I discussed for the TE and the TM. So here you can see the formula, and I also made mention that FC divided by F equals to sine theta, where sine theta here is the tilt angle. And intrinsic wave impedance of TM mode, I gave the formula here, and then I also make it's the same thing like here, it's similar like this. FC divided by F is equals to sine theta. Lastly, I spoke about the first velocity and group velocity of rectangular waveguide, where I gave you the equations for the first velocity in terms of f and in terms of lambda, where Vp is equals to c by 1 minus fc by f. If you can remember, what did I say previously? This is equals to sine theta, which is the tilt angle. And here we have this in terms of lambda. Please take note that as f is increasing, lambda is always decreasing. After that, I give the equation for group velocity, which is similar to this. We have the equation here with fc by f squared, and then we combined the relationship between the phase velocity and the group velocity, where we said phase velocity times the group velocity is equals to c squared. And thank you very much. This is the end of our lecture. Assalamu alaikum.